start. So last time we saw that the exponential function of complex variable is not 1, 1. So let us begin with that observation that e to the power z is not 1, 1. This is actually in contrast with the exponential function of real variable e to the power x, where e to the power x is 1, 1. But if you take a complex variable z, then it is not 1, 1. And in fact, e to the power z plus 2 pi I is equal to, you may multiply this by k for any integer k, is equal to e to the power z for all k in integers. So many points are mapped to the same point. So all these infinitely many complex numbers have same exponential value. So it is not 1, 1. Okay. So let us now write z. So suppose if we write z as x plus I times y, okay, then we know what is e to the power z. E to the power z was e to the power x into cos y plus I sin y. That was our definition of e to the power z. Okay. Now we want to define logarithmic function of complex variable. That is, we want to see the, so suppose w is not equal to 0. Now we are going to define logarithmic function of a complex variable, and we want logarithmic function to be in some sense inverse of the exponential function. But inverse exists if and only if function is 1, 1 on 2. Exponential function is not 1, 1. It is not 1, 1. So in what sense can we define logarithmic function? So it is defined in the following sense. So suppose if you start with a non-zero complex number, okay, then you can express w in the polar form. So I can write w as r times cos theta plus I sin theta. Every non-zero complex number can be expressed in the polar form. So we define log w to be ln r plus I theta, where what is this ln? This ln is real logarithm. So let me write here, is real logarithmic function. We have seen properties of the real logarithmic function. That real logarithmic function is from 0 infinity to r. Okay. And then real logarithmic function is 1, 1 on 2. So this log function we have been using from 11th standard or even before that. So this I am now denoting by ln, just not to confuse with the complex logarithms. This is complex logarithm. So this log has the following properties. This I theta, So what is theta? Theta is argument of w, because w is r into cos theta plus I sin theta. So r is nothing but what? Modulus of w, and theta is argument of w. So you may define for any complex number, any non-zero complex number, w, log w is log this ln of mod w plus I times argument of w. So given therefore any w, we are able to find what is log of w. Okay, because then you find modulus of w, find argument of w and substitute. So for example, suppose I is equal to, if I write I in the polar form like this, that is 1, so mod of I is 1 and argument is pi by 2. So cos pi by 2 plus I sin pi by 2. That is how I is expressed in polar form. So what is log I? Log I is, now this is mod. So ln 1, see, ln of mod w, this is our w. So mod w is 1, so ln 1 plus I times pi by 2. I times argument of w. Now one value of the argument of w is pi by 2. Okay. So this is one value of log I. What do I mean by one value of log I? Because I may as well write I as 1 times cos of pi by 2 plus 2k pi plus I sin pi by 2 plus 2k pi. Do you see this? Because modulus is 1, but the argument, if you change that value by multiple of 2 pi, it represents the same complex number. So I can be always written in this form, and these are infinitely many values of the argument. This is most important point in the definition of logarithm, that the argument has infinitely many values. Argument of a complex number has infinitely many values. So this I, to start with, I wrote this argument. In fact, this is principal argument of I. But suppose if you consider pi by 2 plus 2 pi, that is also argument of I. Alright. So for example, if I draw it here, I is represented by this complex number. So argument is pi by 2. But this pi by 2 plus 2 pi, it will come to the same point. Pi by 2 plus 4 pi, pi by 2 minus 2 pi, pi by 2 minus. So this point has all these infinitely many arguments. That is pi by 2 plus 2k pi. And now, if I write log w to be this, then what will be log I? I can as well therefore write log I as ln of 1 plus I times pi by 2 plus 2k pi. So how many values are there for log I? This ln1 is 0 because this is real logarithm. So this is our usual logarithm that we have seen from 11th standard. So log of 1 is 0. So this term is 0. So it is I times pi by 2 plus 2k pi. So how many values of logarithm I have now? I have infinitely many values of logarithm. So such functions are called multi-valued functions. This log function of a complex variable, log z, it has infinitely many values because this argument may change by integer multiples of 2 pi. So this is pi by 2 plus 2k pi, where k runs in the set of integers, and all these are values of log I. So actually this log of a complex number is a set. It is not a single value, it is set of values. So I can say that log I is this set actually. It is I times pi by 2 plus 2k pi, where k is any integer. K is any integer. So if I ask what is log I, then it has no unique answer. So far, right from school days, anything that is given for evaluation, then all answers should coincide. What is value of this? Then you get same value. But here, this log function of complex variable is not single valued. If I say log I is just I pi by 2, that is I am putting k equal to 0, I pi by 2, then answer is correct. If I put k equal to 1, I times pi by 2 plus 2 pi, that is 5 pi by 2. So log I has infinitely many values. That is I pi by 2, I times 5 pi by 2, and so on. You may also subtract 2 pi, k is in integers. So all these are values of log I. All these can be looked upon as values of log I. So log I has multiple values, and in general for any z, log z has infinitely many values. So this point we want to underline and repeatedly want to see that the log function is not single valued. Okay. So let us see this geometrically. That is, suppose this is complex plane and this is another copy of complex plane. This is I, suppose, and I am considering log function. And what is log I? So if you see, log I is ln 1, that is 0, I pi by 2. So I pi by 2 is suppose here. So this point is suppose I pi by 2. See, this has real part 0, so it will be on y axis. Then I times 5 pi by 2. And this. All these which are differing with a multiple of 2 pi, all are values of log I. All these are values of log I. So log I has infinitely many values like this. And this happens because we want exponential of z inverse to be log I. So all these values will have their exponential equal to I. Their exponential will be I. Therefore, the logarithm takes all these values. Because exponential function is not 1, 1, logarithmic function becomes multi-valued. Is this clear? 1, 1 onto function, then one value in the domain, its image, and then different values have different images. Therefore, inverse is also 1, 1 onto, and under inverse, suppose this point goes here, this point goes here under inverse. Here, this point goes like that under inverse. Now, here in case of exponential and logarithmic function of complex variable, this function e to the power z is not 1, 1. So many values will be mapped to same point. Therefore, log function is not single valued itself. So, actually as such it is not even a function. One complex number gets mapped to several complex numbers. Okay, so it is not single valued. Okay, so log z is the set ln of mod z plus I times argument of z, okay, which you may again write if you want mod z plus I times theta plus 2k pi, where theta is some value of the argument. You may take principal argument and k you may take integers. Okay. Like we took pi by 2 first, and then you may add all multiples of 2 pi, or you can see here itself that if I write small a, that means this is multi-valued argument function. That means this argument itself has infinitely many values. That means you may take any argument and add multiples of 2 pi. So these all values for all integers k, if you put here, whatever value you get here, those complex numbers we call as log z. So log z has no unique value. All these, any one of this value can be called as log z. So answer to the question what is log I, what is log of 2 plus 3i, what is log of 1 minus 5i, the answer will not be unique. The answer will be a set. So this set of values log z takes. Okay. So all this happens because exponential function of a complex variable is not 1, 1. Therefore the inverse is not single valued. So is the definition of log z clear? You take z, then take its modulus. So this is a real number, this is a positive real number, and take its real logarithm. So this ln you should not confuse with this log. This symbol I have reserved now for complex logarithm. This ln specifically I have written for real logarithm. So this mod z is positive real number and this is real logarithm, and this argument z is the angle made with the positive x-axis, angle of z with the positive x-axis. But if you add 2 pi, again add 2 pi, or subtract multiples of 2 pi, add multiples of 2 pi, it remains same. Okay. So therefore all these values are values of log z. So because of the multi-valued nature of argument, we get multi-valued nature for the logarithm also. So logarithm is multi-valued because the argument is multi-valued. Okay. And then the function logarithm is defined so that it will satisfy certain properties. So first thing you have to always remember that if I write log z, then it is set valued and it is this set. Okay. So let us find logarithms of some complex number as examples. Okay. So let us find actual logarithm values of some examples maybe. Okay. So I want to take you to in the notes, okay, on this page where I have defined the logarithm function. So let's see. Yes, this logarithm function is defined here, and yes, the log z is the set of complex numbers. So now what I said just now is there on the screen in front of you. Okay. So let us now find out for some specific complex number. So suppose if I take 2 plus 3 pi I, that is my z suppose. I want any non-zero complex number, then I can find its logarithm. I have defined it. Only condition is that it should be non-zero. Because exponential function does not take zero values, the logarithm of 0 is not defined. So log function is defined on punctured plane, that is at 0 it is not defined. So this is not 0, so I can find its log. Is this clear? This complex number I can find log by definition. So I will now apply definition. You see now. So log z is, yes, no, wait. I have written this is like this. I want to write like this. So let me correct it. So I want 2 times cos 3 pi plus I sin 3 pi. Whatever I wrote at that initially I can also find, but first of all this is easier because I want to express in the polar form. So now I have written like this. So I want it like this. So mod z is 2. Is this clear? Because we write r into cos theta plus I sin theta. So this is modulus of z. And argument of z, one argument is 3 pi, it is as given like this. But even if I write 5 pi, it will represent same complex number. Okay. If I add 2 pi to this, you get same angle. Okay. If you take this some complex number and add 2 pi, you will get same angle. Add any multiple of 2 pi, you get same angle. So now log z is ln of mod z, but that is ln of 2 plus I times theta plus 2k pi. So I can write 3 pi plus 2k pi where k is integer. So all these are values of log z, all. So that is ln 2 plus I times 2k plus 3 times pi, where k is integer. Do you see this? That is, these are values of log z. I am not saying this is value of log z. These are values of log z, that there are infinitely many values of log z. Why there are infinitely many? Because this k is varying. You may take k equal to 0. Then I get value ln 2 plus I 3 pi. If I take k equal to 1, I get 3 plus 2, 5 pi. ln 2 plus I times 5 pi. I may write k equal to minus 10. So 2 times minus 10 is minus 20 plus 3, minus 17. ln 2 plus I times minus 17 pi. So all these are values of log z. So log z has infinitely many values. Is this clear? So only thing is you have to first of all write the complex number in the polar form, then you get what is r and what is theta, and then write log z like this. So let us find few more logarithms. So suppose if I want to find the log of minus 1. Now remember, minus 1 is a real number, but we cannot apply real logarithm to minus 1 because real logarithmic function is only for non-negative real numbers. Our ln, real log, is not defined at minus 1. So log of minus 1 as our old logarithm, it doesn't make sense. The logarithm that we have been learning from 11th standard, or maybe before that, in school also we find logarithms. But that logarithm is only for positive real numbers, remember. We never encounter logarithm of a negative number. So log minus 1 does not make sense as real logarithm, though minus 1 is a real number. But minus 1 being a real number can be looked upon as a complex number, and it is a non-zero complex number. And non-zero complex number, then our logarithm function of a complex variable is defined for a non-zero complex number. Except for 0, complex logarithmic function is defined at every point. So you can locate this minus 1 here. So minus 1 can be looked upon as minus 1 plus I times 0. So it is a complex number. And except for this point origin, log of every complex number is defined. It has infinitely many values, that is alright, but we can find out log. So we can find out log minus 1 treating minus 1 as a complex number. Okay. So minus 1 is looked upon as minus 1 plus I times 0. Now we have to express it in the polar form. So what is polar form of minus 1? So in the polar form, what do you get? Minus 1 equal to mod minus 1, that is plus 1, into argument of minus 1 is pi. Argument of minus 1 is pi. Principal argument. You may write pi plus 2 pi, pi plus 4 pi, that is alright. But do you see this angle made with this positive x-axis? With this minus 1 is on the ray, which makes angle pi with the positive x-axis. So, alright. See, this tan inverse of y upon x could be confusing because this is x, this is y. Now if you try to find out argument by tan inverse of y upon x, it is tan inverse 0. So you may write tan inverse 0 equal to 0, but the argument is not 0. So you may think of this as cos inverse of x upon r and sin inverse of x upon r, because polar coordinates are found by x equal to r cos theta, y is equal to r sin theta. Okay. So this x upon r, so minus 1 upon modulus. So what is modulus is 1. So minus 1 upon 1 is 1, and cos inverse of that. So cos inverse of minus 1 is pi, and sin inverse of y upon r. So sin inverse of 0. So you want to find theta such that cos inverse of 1 is, cos inverse of minus 1 should be equal to sin inverse of 0. And that is actually one of the values is pi, because cos pi is minus 1. So argument is cos pi plus I sin pi. Cos pi plus I sin pi. Once I get r and theta, I can find values of log z. So log of minus 1 is equal to log r. So this is real log, ln r, because this is always positive, we can take real log, plus I times theta plus 2k pi. So I can write 2k pi, where k is any integer. So how many values of logarithm I have found? Infinitely many. Every time we will get infinitely many values. Log z has infinitely many values. Okay. So this is log of minus 1. That is, it is ln r plus 3k pi I. Ln r means r is 1 here. Actually r is 1 here. So that this is 0. So log of minus 1 is equal to, this is 0 and 2k plus 1 pi. So I times 2k plus 1 pi, where k is integer. So you may put k equal to 0, so it is I pi, k equal to 1, so it is 3 pi I, k equal to minus 5, so it is minus 10 plus 1, minus 9 pi I, and so on. You may put any integer. All these are values of log minus 1. Clear? So log function is multi-valued. Now, we have defined log. Okay, let us find one more. Let us do one more example. That is important. Okay. So suppose if I want to find log of 2. Find log of 2. Now you may ask that this is positive real number, and we already know what log 2 means, because our old logarithmic function, real logarithmic function, is defined at 2. So there is already some meaning for this. Unlike this log of -1, which does not make any sense if -1 is treated as a real number. Because for negative real numbers, the real logarithmic function is simply not defined. But for positive real numbers, the real logarithmic function makes sense. See, our real log function, which I have called now ln, is from 0 infinity to r. So if I take a positive real number, the real logarithmic function does make sense. So this log has certainly one value we know. We know in the sense, we know the definition of logarithm of a positive real number. But now again, if I look upon 2 as a complex number, so 2 is a complex number also, is a complex number. Two equal to 2 plus I times 0. It is here. So suppose this is 1, this is 2. So this is 2 plus I times 0. Its modulus is what? This modulus is 2. So mod of 2 is 2. And argument is what? Argument is 0, because this is on this positive real axis itself. We find angle made with the positive real axis, but it is on this positive real axis. So argument is 0. Okay. Or in other words, you may consider again cos inverse of 2 upon 2, that is x upon r, and sin inverse y upon r. So cos inverse x upon r is cos inverse 1 and sin inverse 0. So the solution is theta equal to 0 or theta equal to 2 pi, 4 pi, so on. Once you find one argument, then there are infinitely many arguments, that is 2 pi, 4 pi, minus 2 pi. So this you can also see, this angle is 2 pi, this angle is 4 pi, whatever. But we have this one argument, and then we know that because of this itself, we are getting several values, because now I will add multiples of 2 pi while finding logarithm. So log 2 is equal to ln mod z, that is ln 2 plus I times theta, that is 0 plus 2k pi, where k is integer. So that means ln 2 plus 2k pi I for integer k. Now see, very important point, that this log 2 has unique value considered as a real logarithmic function, because 2 is a real number also. So when treated as a real number, it has a unique value, because this real function is single valued. So given 2, it will assign a unique real number as log 2. But now this log 2 has infinitely many values. Do you see this? This log 2 has infinitely many values. So log 2 apparently has two meanings. Log 2 has two meanings apparently. Now our original log 2, that is ln 2, can be recovered by putting k equal to 0. So out of infinitely many values of log 2, so when log 2 is considered as a complex number, it has infinitely many values, because for any complex number, logarithm has infinitely many values. So when 2 is treated as a complex number, its logarithm has infinitely many values. And one of these values is ln 2. See, I can put k equal to 0. So I get ln 2 in that case. So one of those infinitely many values is our real logarithmic value log 2. Do you understand this point? Log 2, let me repeat again, listen carefully. Log 2 is already well defined. You have used log 2 in several experiments in physics, chemistry, maybe in mathematics, in computations we have used. From 11th standard you use log 2. And it has unique value. There is some real number which is log 2. When 2 is treated as a complex number, which I have done here, I get infinitely many values of log 2, and these values I have written here, that is, it is ln 2 plus 2k pi I. So this log 2 has infinitely many values when treated as a complex number, and one of those infinitely many values is actually our real logarithm of 2. That is the point, okay, which is this ln 2. Okay. So just watch this equation carefully once. Read this. Okay. Now let us see some properties. Let's see some properties now. First is e raised to log z is equal to z. Now each time you have to remember that this log z is not just one value. So I have to say whether this equation is true for some value or all values, or what do I mean by this, because this itself has this has no unique value. So it has infinitely many values. So when I am writing equation, I must be careful. So I must write that this is true for all values of log z. Why? Because see that suppose, so let me prove this. So if z is equal to r cos theta plus I sin theta, then what is log z? Log z is ln r plus I times theta plus 2k pi. Now you know that k is integer, and e raised to log z. So what is my definition of e raised to z? It is e raised to x into cos y plus I sin y. So now this is x plus I times y. So this is e raised to ln r plus into e raised to x into cos theta plus 2k pi plus I sin theta plus 2k pi. But what is cos of theta plus 2k pi? It is cos theta. Sin of theta plus 2k pi, it is sin theta. So it is, and what is e raised to ln r? It is r, because this is now real exponential and real logarithmic. So e raised to log z is equal to e raised to log z is equal to e raised to ln r. Do you see this? E raised to ln r, that is r. So e raised to log z is equal to r into cos theta plus I sin theta, which is nothing but z. That z was given to us. So e raised to log z is z. No matter which k you take, no matter which value of k you choose, theta plus 2k pi, but whatever value of k you take, you get e to the power log z is z. Of course, if you write log of e to the power z, then there will be problem. Log of e to the power z, okay. First of all, it has infinitely many values. When I take logarithm of any complex number, it has infinitely many values. So I cannot write it is z, okay. So this is certainly not z always, okay. So this has infinite values, infinitely many values. And of course one of the values will be z. Of course one of the values will be z. Why? Because let's see, what is e to the power z? It is, so log of e to the power z will be log of e to the power, okay, it is log of e to the power x into cos y plus I sin y. Okay. Now I look upon this as polar form. So this is r into cos theta plus I sin theta. So modulus of this is e to the power x and argument is y. So when I take this log, I get what? Log of, so now ln of modulus, that is ln e to the power x plus I times y plus 2k pi, k integer. So log of e to the power z has these infinitely many values. But if I put k equal to 0, I get, now see, this is ln e to the power x is x plus I times y plus 2k pi. So this is x plus iy plus 2k pi I. So it is x plus iy was z. So z plus 2k pi I. So log of e to the power z is nothing but log of, do you see that it is z plus 2k pi I. So log of e to the power z is z plus 2k pi I. So one of the values is z. If I put k equal to 0, I get z. So this log has infinitely many values and one of the values is z again. Remember always this, that log has infinitely many values. When you write any equation involving logarithm of a complex number, you have to be careful and you have to specify with how this equation makes sense. In what sense you have to interpret that equation. For example, if I write log of z1, z2, then I want to see that it is log z1 plus log z2. Log z1 plus log z2. This is true, but this equation again has to be interpreted in a certain sense. That means out of these three quantities, this log and this log, each has infinitely many values. So this is a complex number, so this logarithm has infinitely many values. This is a complex number, this logarithm has infinitely many values. And this is a complex number, this logarithm has infinitely many values. If I take some particular value here and a particular value here and add, I get certain particular value of log of this so that the equation will hold. That is how this equation has to be interpreted. I will repeat again. This equation, it looks like our old equation of logarithm with real variable. Log of x1, x2 is log x1 plus log x2. That is absolutely true. There is no question of interpreting that. For any positive real numbers x1, x2, log of x1, x2 is log x1 plus log x2. Now if you take complex variables, then this equation log z1, z2 equal to log z1 plus log z2 needs interpretation because the value is not unique. So these are infinitely many values, these are infinitely many values. What does this equation make sense then? So the equation makes sense in the following way, that you choose one particular value out of infinitely many, you choose any particular value, add these two, then you get a complex number. Then you will always find one particular value of the left hand side which will coincide with that addition. That is how one has to interpret. Okay? And this equation will certainly hold because you take Z1, so I will just tell you this proof, see here. So concentrate, if I write Z1 equal to R1 cos theta 1 plus I sin theta 1 and Z2 equal to R2 into cos theta 2 plus I sin theta 2, then what is Z1 Z2? Z1 Z2 is R1 R2 cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Okay, what is log of that? It is ln R1 R2 plus I times theta 1 plus theta 2 plus 2k pi. Remember, purposefully I am telling all this orally. I am going to write it, but you concentrate. Remember that when something is told to you like this, you should be able to concentrate and grasp that and try to write it later on also. That is also a good exercise. So, shall I leave the proof of this to you? I am telling this orally and then you write down later on. Is it alright? That will also help. So, now see, how do I prove this? Z1 is R1 cos theta 1. Any complex number you want to find log, then you write in the polar form. So, write polar form of this, you will get polar form of this. So, start with Z1. Z1 is suppose R1 cos theta 1 plus I sin theta 1. This is R2 into cos theta 2 plus I sin theta 2. Product Z1 Z2 is R1 R2 into cos of theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Now this log, if you apply definition, it is ln R1 R2 plus I times theta 1 plus theta 2 plus 2k pi. This will be okay. Now that if you simplify, it is ln R1 plus ln R2 plus I times theta 1 plus theta 2 plus 2k pi. So that is ln R1 plus I times theta 1 plus ln R2 plus I times theta 2 plus I times 2k pi. So it is log Z1 plus log Z2 plus 2k pi I, okay, and then if you choose k, then you can choose this, okay. So this equation you have to interpret in a particular way to get this. So the point number 4 I have written there. All the 3 logarithms involved in the equation take infinitely many values. If 2 of the 3 values are given, the third will satisfy the equation. Okay, so that is how it is. Now, let me go to, alright, so maybe the next page, if you go to next page of these notes, then there are some more properties written. Log of Z1 plus Z2 is log Z1 minus log Z2. Now this also has to be interpreted in a similar way. That means if I take Z1 upon Z2 and take logarithm, then the logarithm will have infinitely many values. So let me write it here. So log of Z1 by Z2 is log Z1 minus log Z2. This needs also interpretation. As it stands here, so this needs interpretation. So you have to interpret this. And how do you interpret this? This Z1 you take R1 cos theta 1, Z2 R2 cos theta 2. So it is R1 upon R2 cos of theta 1, so you multiply by theta 1 cos theta 1 plus I sin theta and so on. So it is cos of theta 1 minus theta 2 plus I times theta 1 minus theta 2. And then ln of R1 R2 is ln R1 minus ln R2 plus I times theta 1 minus theta 2 plus 2k pi you will get. And then these have infinitely many values, this has infinitely many values, and this has infinitely many values. So the interpretation is that if one particular value you choose, then you get one value, this. And property number 6 is, as you can see there, that for any complex number z, the equation z to the power n equal to e to the power n log z, where this holds for any value of log z. Okay. So z to the power n is e to the power n log z. Now this will hold for any value of log z. So whatever value of log z you may take. Okay. How to prove this? So because you can see there, that is, if you take z is equal to r into cos theta plus I sin theta, okay, then what is e raised to n log z? So first of all I will find log z. By definition it is ln r plus I times theta plus 2k pi. Now you know this definition. Now I will multiply this by n because we want to find n log z. So n log z is n times ln r plus I times theta plus 2k pi. Okay, this is n log z. This is log z. I have multiplied by n. Okay. So now I want to find e raised to this. But e raised to any complex number is what? E raised to any complex number is, so this is x plus I times y. So e raised to x into cos y plus I sin y. So you apply the definition now. So n log z I will write again. N log z is n times ln r. I multiply that n inside plus I times n theta plus 2k pi. Now I will take exponential. E raised to n log z is equal to, now this is x and this is y, and e raised to x plus iy is e raised to x. So e raised to n log r, n ln r, this is real log, into cos of n theta plus 2k pi I, cos of n theta plus 2k pi plus I sin n theta plus 2k pi. This is cos of n times theta plus 2k pi. This is n times theta plus 2k pi. Okay. So cos of sin of n times theta plus 2k pi. But e raised to n log r is r raised to n. So it is r raised to n, and cos n theta plus n 2k pi. But if you add a multiple of 2 pi, cos remains same. So it is cos n theta plus I sin n theta. But this is nothing but z raised to n. So z is r into cos theta plus I sin theta. Then z raised to n is r raised to n cos n theta plus I sin n theta. So this is z to the power n. So e raised to n log z is z to the power n. I have proved. Okay. This is important property because when we will go to the complex exponent function, that is z to the power w, then we will need this for just reference, that is e raised to n log z is z to the power n. Remember, this is z to the power n where n is integer. In general, later on we want to define z to the power w, where w is not just integer, it is a complex number. It is a complex number. Okay. So thus we want to come back to that later on. Next property 7 that is written there, if z is not equal to 0, the equation z raised to 1 over n equal to e raised to 1 over n log z holds for any integer n. I am reading the notes that are there in front of you, so just go through that. If z is not equal to 0, then the equation z raised to 1 over n equal to e raised to 1 over n log z holds for any integer n, and the proof is given there. So see the proof there. See the proof written on the white screen in front of you. So 1 over n log z is 1 over n log r. That log r here in the classroom I have denoted it by ln r. So 1 over n ln r plus I times theta plus 2k pi. K integer. So e raised to 1 over n log z, now I have taken exponential on both sides, is r raised to 1 over n. Do you see this? Do you see this whatever I am reading here from the notes? Yes? So e raised to 1 over n log z is r raised to 1 over n, because 1 over n log r is r raised to 1 over n. Cos of theta plus 2k pi upon n plus I sin theta plus 2k pi upon n for k in z. The right hand side gives only n distinct values by putting k equal to 0 to n minus 1, which are nothing but nth roots of z. See, this is nothing but the de Moivre's formula for finding nth roots. So do you see the right hand side written there? Do you see that? That is r raised to 1 over n cos theta plus 2k pi upon n plus I sin theta plus 2k pi upon n. And if you take k equal to n, then it is again theta by n plus 2 pi. So you will get again same values if you change k from n. So this right hand side has exactly n distinct values, k equal to 0 to n minus 1, which are nothing but nth roots of unity. So you will get that z raised to 1 over n is e raised to 1 over n log z. So this formula which I have written here, z raised to n is equal to e raised to n log z, also holds for fractions, that is z raised to 1 over n is e raised to 1 over n log z. And there itself on those notes I have written it for negative numbers, that is suppose if n is negative, then let m equal to minus n, so that m is positive, and z raised to 1 over n is then z raised to minus 1 over m, 1 over z raised to m, but m is positive, so you apply this formula and you will get e raised to 1 over m log z, that is e raised to minus 1 over m log z, that is this. So this actually holds not only for positive integers but for all integers n. So in particular it will hold for rational numbers, any. Clear? Because this is anyways true, this is true. Now take mth power on both sides. So it is e raised to m by n log z. Because this z goes here, only this n comes here. So if I take now mth power, this m will come here. So is this clear? So this is true for any rational number. So I can write that z raised to p is equal to e raised to p log z for p in q, that is any rational number. And this is actually the motivation for defining z to the power w, which we may come to the definition of z to the power w in the